Okay, here's the second side of Archimedes' principle 2. They say, here's a glass of ice water with an ice cube floating in it. Draw the water line after the ice cube melts. Will the line rise, fall, or remain the same? Oh, good question. Will because right now it's displacing water. As it melts, will it displace less water and it falls? But it becomes water, so will that cause it to rise? Do those two things cancel out and it stays the same? So one thing is, let's just pretend that this is a big glass of water, just to make these numbers easier, and a big thing of ice. Let's just say that this is 1 liter of ice, or excuse me, 1 kilogram of ice, I mean to say. So if it's 1 kilogram of ice, it's got to push 1 kilogram of water out of the way in order to float, because we know that the buoyant force on it has got to be equal to the force of gravity on it, because it's floating. Well, 1 kilogram of ice, when it floats, becomes 1 kilogram of water. So it's currently pushing 1 kilogram of water out of the way, but when it melts, it will become 1 kilogram of water. So in a sense, it will fill in its own hole that it filled up there. So it stays at exactly the same level there. The air-filled balloon is weighted so that it sinks in the water. Near the surface, the balloon has a certain volume. Draw the balloon at the bottom inside the dashed square down here, and show whether it's bigger, smaller, or the same size. Well, because it's a gas, it will be pressed in more and more by the greater pressure the deeper we go. So when we get to the bottom, it is going to be smaller up there. The gas will be denser. Since the weighted balloon sinks, how does its overall density compare to the density of water? It must be a greater density, and that is why it sinks. As the weighted balloon sinks, does its density increase, decrease, or remain the same? Its density will increase because the gas will be pushed into a smaller volume there. Since the weighted balloon sinks, how does the buoyant force on it compare to its weight? So the buoyant force must be less than the weight, and that's why it sinks. As the weighted balloon sinks deeper, does the buoyant force on it increase, decrease, or remain the same? Well, it's taking up less and less space, so it's displacing less and less water, so the buoyant force will decrease there. What if you did the exact same thing, but you did it with a stone? So rather than a balloon, we just have a solid stone here that can't be compressed. So how would your answers change here? So answer A would still be, the stone would sink, so it still has a greater density overall than the balloon. As it sinks, does its density increase, decrease, remain the same? The stone's density is going to remain the same. So it might theoretically at the bottom of the ocean be compressed a teeny bit, but it's basically the same. Since the weighted balloon sinks, how does the buoyant force compare? I keep saying weighted balloon, but the stone. Since the stone sinks, does the buoyant force on it compare to its weight? So the buoyant force must be less than its weight. That's why it sinks. And finally, as the stone sinks deeper and deeper, does the buoyant force on it increase, decrease, or remain the same? Well, its volume won't be changing, so the amount of water it pushes out of the way won't be changing, so its buoyant force will remain the same there.